Okay. Okay. Well, thanks everybody for coming. My name is Eric Erlandson, and I'm a software engineer at Red Hat, and I'm here to talk to you today about integrating Open Data Hub with Ray. Or you could think of it as Jupyter and Ray in the cloud. So the basic landscape to talk, I'm going to describe like what Ray is and how it works. It's 10,000 meters, and then I'm going to kind of put Jupyter and Open Data Hub like into context about where it's coming from and why, and then I'll describe like how I get Ray on ODH to work, and then do a little demo, and then just close with some of the relevant community collaboration. So Ray was designed to sort of like occupy a niche on the spectrum that you could say is sort of like, you know, at a significantly higher level than something like OpenMPI, which is of course extremely low level, but give you a little bit more fine-grained control of what kind of parallelism you actually have than something like Apache Spark. So in Ray, there's two kinds of things you can parallelize. There are tasks, which are just like you know, executing a function, and actors, which kind of act like parallelizable services. And its corresponding programming model is actually quite easy to use if you have any kind of you know, Python function. You can simply add this @Ray remote decorator, and Ray will, you know, wrap it in some parallelizable code. And similarly, if you have a class, you can do exactly the same decorator. And now you have something you can deploy into Ray as a running service like object. So if you've ever worked with something like Apache Spark, that's probably familiar to you. It represents all of its computations as a declarative DAG. And so by declarative, what I mean is you build up the computation, you know, with calls, but it doesn't execute until you actually tell it to. So here you can see we're basically building up a little tree that is going to add up a bunch of integers, the most over-engineered summation of integers you may ever see. But basically saying, hey, I'd like you to set up a compute where you add integers 1 and 2, 3 and 4, and so on. And then I'd like you to, you know, add up the intermediate ones. And then finally, at the very bottom, when you say ray.get, you know, Ray goes off and says, okay, now you want me to compute something, and I'm going to unwind this DAG for the compute and send you back the results. And I took this particular example in the diagram, this nice blog post by Robert Ishihara. If you want to go check it out, it's a nice write-up. So yes, that's a great idea. Ray's data model is basically a typeless object store, which is implemented by Plasma. Now, at the time when Plasma started, it was actually part of the Ray code base, but they've since exported it to Arrow, actually. So it's now the Plasma stuff you can find under the Apache Arrow project. So like a lot of things in Python, it's typeless and schemaless. It's just data that you push up there. it is designed to be local first, which is to say it will try to use, if you have a computation that's using data, so I'll look to see if the data is available locally first before it pulls. And so, as long as things are staged properly, it can be quite efficient. Ray's scheduling model is similar. It will try to execute the functions you give it locally first. It only submit to the global scheduler. Can't service a compute and has to try to do it somewhere else. There are many libraries, like the big five are Ray tuning for like hyperparameter tuning. It has scalable reinforcement learning and distributed training with standard like stochastic gradient descent. It allows you to actually serve models if you train using the Ray serve library. And a new addition, relatively speaking, is Ray datasets. So I was just telling you about how it's native object store is sort of like typeless and schemaless, but Ray datasets are sort of like native data frames. So if you're working with columnar data like data scientists we often do. There are tons of integrations. They're like you can integrate Ray easily with XGBoost, Dask, PyTorch, sklearn, and some of the more specialized libraries like Spaceheap, Hugging Face. The bottom is a URL which you can look at for looking at all of them. And so one thing about all these you might have noticed, of course, is all these are things that people already use on Jupyter. And so that we could, if we integrate it properly, get literate programming and interactive iterative development with Jupyter, but using Ray as a parallelizable compute backend. Of course, these are both tools that run on Kubernetes, or in the case the demo that I'm going to be doing, OpenShift. So when I was first attempting this integration, you connected to a cluster using ray.init, and it had a strange limitation where sorry about the feedback. It had a sort of strange limitation where you could only connect on the physical node that the head node was running on. And so, like, if you wanted to do this, you would have actually had to like install the Ray head node and Jupyter onto the same pod. And so this is like obviously architecturally not very convenient. However, not too long afterwards, they created a new utility, Ray.connect, and Ray.connect allows you to connect the way you'd really like to, which is to say you have some application like a Jupyter environment, and you connect remotely to the Ray head pod. This allows you to stand up the Ray cluster separately and connect it from the inside. Now, they keep evolving this, and so now Ray.init, which used to work the wrong way, is now the new standard, which was the old standard, but now it connects again using this proper full remote connection facility. So that's been something as fundamental as like how you connect to the Ray cluster. They keep like changing that, but now it's back to good old ANIT. So in my case, I wanted to sort of like consume Jupyter via Open Data Hub. And there are a few reasons for that. Open Data Hub, first of all, is an open source downstream of Kubeflow, and so it kicks off the LXC open source tooling box. It is a reference platform, which is to say it acts as like a repository of standard data science tools many people like to use, and allows you to deploy them easily as like a reference stack into the cloud. And it's nicely federated. So like while you can easily install all these different tools via Open Data Hub. They're not super tightly integrated, and it also, because it's all running on OpenShift, makes it easy if you need to add other kinds of tooling into it, and you're not going to break its model. Open Data Hub, covers most of the phases of a machine learning workflow, all the way from setting your business goals to ETL, preparing data, training, through actually deployment and monitoring. And along the other axis, it also basically covers the corresponding persona. So, stakeholders, data engineers, data scientists, and the DevOps folks and IT operations who may be helping you actually run your models. And you can see that, today I'll be primarily talking about Jupyter, which is right in there, but because this is in an Open Data Hub environment, all these other tools are available through the Jupyter consultant. So at Red Hat, we actually use Open Data Hub. There's been studies of application log analyses and collecting cluster metrics via projects like Operate First. And also internally, some of the customer support data is being processed. So it's a tool that we actually use. So now I'm going to start describing how this is actually working. And I'm going to start with an analogy. Existing integration, which is the Spark on Open Data Hub. So if you've ever used ODH Jupyter Hub Launcher, you bring it up and you can pick an image and tell what size it is, and you kick it off. And when you kick it off, the launcher, first of all, as it always does, spins up a Jupyter environment for you. But there are some other things it can do if you configure it. So you can also configure a Spark single user profile, and ODH Launcher will detect the presence of this out on the cluster, and it will look for some resources to spin up, and the resources are described via what are called cluster service templates. And it's basically YAML with templatable Jinja substitutions. And so those objects you can configure to do something like stand up a Spark cluster for you. And then once you get into the Jupyter environment, the cluster is there and available for you to connect to and use. The single user profiles and the corresponding template objects are nothing but config maps that sit out on the cluster. And so it made me wonder, well, if I can describe objects that stand up a Spark cluster, why maybe I could also describe something that stands up a Ray cluster and integrate the same way and give you self-service, personalized Ray clusters you can work with. And we all love YAML, right? But I wanted to show you this not because I want to actually expose you to YAML, but just to show you that these really are just very standard objects that you can create. Here we have, the profile for a Ray ML notebook, and I described some things like the Ray cluster and some resources. And the bottom, I describe how you might fill in array cluster environment variable for the notebook. And similarly, that points to a bunch of template objects, and so all on the second config map, you can see nothing particularly special about it. You can see things like username, how to generate special labels, and otherwise standard things that Ray clusters like to know about, like how many workers and upscaling rates and stuff like that. And so now I've described you sort of how this is all happening, and do a little live demo on our cluster. And I just wanted to pause to mention that the person who took my original work and has totally it and added all the latest Ray features and the updated images is Michael Clifford. So the demo you're about to see is thanks to Michael for putting it up on our data science cluster. So here we have a Jupyter environment. And because it takes a few minutes, I'm not going to show you the process of logging into the launcher. But I logged into the launcher and spun me up the Jupyter environment. You can see it has a bunch of and Ray tune and other stuff already pre-installed on the image. Again, Michael updated all those images in the soft build. And so we're going to port these things. And here I mentioned the Ray cluster environment variable. This again is like basically preset for you. You can see it. It's just basically a name of a service that's sitting out on OpenShift or Kubernetes cluster so that it can connect it. So here we'll do the Ray init command. Standard port, and it connects, and gives us back a this object describing its parameters. So you see the latest version is 1.13. So I want to actually, at this point, it's kind of arbitrary. In a sense, I just showed you like the integration network. However, it will actually do something with the Ray cluster. So I'm going to use with the standard sklearn generate some arbitrary classification data that we can use. And we will actually run a bit, just a baseline to show you what should be run SVG and fit a model to it and report like that it's running getting 50% accuracy on our synthetic data. So now, that's of course the standard thing you might do in Jupyter. Now we're going to try to do the same thing using Ray tune or hypertune. And we'll create ourselves an objective function to send to it. Those of you who are perceptive might notice that I've actually stuck my training data in the closure of the function, which is not something you're typically going to do, but it works for a demo. Normally, you would actually stage this in sort of like a Spark-like way using the Ray dataset model to make things actually efficient for large-scale data. We'll define hypertuning search space using the standard alpha and epsilon parameters. So you can see our grid is six elements into it if we multiply it out. And now, with our objective function and the search space, we will kick off a tuning run. And now here, we're actually sending this stuff off to Ray and telling it to actually search over our space and send back, the best possible result. We'll complain a little bit, but it will actually work. So you can see the first thing is one of these things is running. The Ray head node is always up, so it immediately got a job running on that node. You can see it asked for all 6 of those grid elements, and currently it doesn't have them yet. So let's keep running. Now here things get interesting. You can see it's actually acquired 4 of the 6. And it's not going to acquire anymore because we asked it to actually use GPUs, and our cluster only has 4 GPUs. And so the Ray operator is very adaptive. It will just keep trying to get stuff. And if it makes a request to the Kubernetes or OpenShift scheduler for more worker nodes and it can't be satisfied, well, it's okay with that. So we would like to get to 6. It's not going to have them. That's okay. We'll keep running. It's very talkative. And so anyway, in just over a minute, it gave us all the results. And of course, this is a very small set. It is entirely possible because of the way I designed this data and stuck it in the closure, and it's actually super small. It would have been faster, frankly, to probably run locally. But in the real world, of course, we have much larger models and much larger data, and so parallelizing it can be a big win. So anyway, we can ask the object that it returned to tell us what the best result it was, and it said, oh well, I got my best result using an alpha of 1 and epsilon of 0.1. And so what I can do is just quick train with those parameters one last time and see what I got. And so here I got 88.8% accuracy, and compared to the first guess, it's slightly better. So our hypertuning works. So here's an example of using the power of Ray from a nice, convenient self-serve future environment to parallelize the machine learning workflow. So as I mentioned, Ray has tons of integration, prefab for you that's easy to pip install or pre-stage on your container images. And the nice thing about this is that you can use the same Ray cluster to run all these. So you can build up pretty complicated notebooks or complicated workflows, all talking to the same cluster and parallelizing. So you have a unified scaling environment for your data science. And of course, unification also typically means simplification. You don't have to stand up a lot of specialized engines like a special Dask engine or XGBoost parallelizer. You can basically tell it all of it to talk to the Ray cluster and use that for the engine. It's a much nicer, cleaner environment. So a lot of this work I did, especially early on, was courtesy of the ODH installations with the Massachusetts Open Cloud. Thank you, MOC. And also in cooperation with the Operate First project, where of course they're trying to take the principles of developing software in the open and extend them to operating software and services in the open. And this particular deployment I'm describing here no longer exists because the actual cluster went away. It was the old zero cluster for those of you who work on the MOC. But you can see here I was able to use the Operate First project to describe everything I just showed you as a bunch of pull requests. And once I had gotten them merged and redeployed, the demo that I showed you was actually running up on the MOC. So what's going on for the future? I want to actually redeploy Ray plus ODH on the MOC on the new clusters that they stood up out of the smog. We would like to at some point take the Ray operator and put it in the official operator catalog or something that they can install via the operator lifecycle manager. And some things that have happened since the last time I delivered this talk, we do have properly maintained Ray images on Project Auth. So they're standard builds and they're updated. And we have community use cases through Jupyter, again, courtesy of Michael Clifford. I would like, on our roadmap, hopefully for this quarter, is to get an actual formal integration with Open Data Hub. So to basically make what I showed you an official part of the overlays that you get with the operator. And also this quarter, we're exploring taking models to train, deploying them to edge devices. So possibly running Racer at the edge or alternate model service architectures. And those of you who are familiar with the Open Data Hub world, everything I just described to you is done with the Open Data Hub, Jupyter Hub launcher. Now, they are actually going to be moving away from this old launcher to using Integrate Notebook Controller. And so we're going to explore how to do what I just described here, single user profiles via the notebook controller. And that's the end of the talk. I encourage you to, once we get this back up on MLC, play with Ray. If you have any comments or questions or want to reach out, send an email to myself or my Clifford. And, thanks, everyone. Yep.
First of all, this is awesome. This is really data. It's good. But what I'm really confused about is, so you expanded the rating by 14 the object class by the node. Right? So the kind of, if you have a reproduce, for example, it's really hard to reach that. It would be all locked down and you have that, when you have that continuous. So when you want to have a persistent way environment to make it that
Right.
they can all keep working. Ray is easy. Why did you say that?
That's a great question. And first of all, obviously, you saw I was just connecting to the one it made for me, but you could stand your own up and connect to it too. Oh yes. He was asking like why. The question was why would I give each user their own Ray environment instead of a large persistent cluster that people could connect to. And the first part of the answer to the question is if that's the way you actually want to work, you can. It's easy to produce these clusters using the array operator. You just produce array cluster, a custom resource, and it spins it for you. The reason I didn't do it that way is because I actually like sort of like pushing. I prefer to push the multi-tenancy onto the platform. So like, while array can be multi-tenant, my experience with trying to use these kinds of platforms as multi-tenant is that they don't always implement like the scheduling and the sharing. And once you become multi-tenant, you're like signed up for a lot of stuff. You got to like be able to manage multiple people's jobs and like how you allocate the resources. And so like a lot of these projects, while they support that, they end up not supporting it well because it's kind of like the writing your own crypto problem. So like I'm pushing it, doing it this way. I'm pushing it onto OpenShift and Kube, which already have highly developed scheduling and resource sharing, and that's what I think is good about it.
Yeah, I like that a lot. The problem with it is that Ray and physically stays in the memory of the speech. So it's going to hold on to it for a long time.
Well,
hold on to it for nothing.
It scales itself down. Like you saw how it acquired those workers. You can configure it, like after a certain period of idle time, it just spins them down again. So it won't hold on to them forever. However,
if you have an OpenShift cluster for classroom, it's really saying that for classroom data, it makes sense to just share that.
Right. Excellent.
Hello. Can you all hear me fine? Hello. Yeah, this is working. This is working. Okay. Yeah. Hello. Shall we start? Okay. Hello, everyone. Thank you for coming to our talk today. It's about when to stop, optimize, test runtimes using AI for CI. It's a bit of a mouthful, but we hope to explain everything at a very high level to give you an overall picture of what we're trying to do in this particular project. Before we get started, just by a show of hands, how many of you are developers or have pushed code somewhere? Okay, almost everybody. So oftentimes when we are working and dealing with code, whenever we try to push it to production, I'm sure all of us have faced a time where we have sort of been subjected to a lot of tests and a lot of automated builds checks that happens before your code is actually deployed onto production. Now, oftentimes these sort of checks that happen are what we call as CI/CD tests, which are nothing but your continuous integration and deployment checks that happen against your code. And these typically take a lot of time to validate your code before it actually accepts it into the code repository. And oftentimes that can be a bit of a bottleneck for your process and also can consume a lot of resources on your systems. So we want to use AI and machine learning to sort of help enhance this process and to eliminate these long test running times. And hence, we want to optimize these test run times. And that's what we're going to talk about today. And to get started, I'm Hema Viradi. I'm working as a data scientist at the emerging tech group here at Red Hat. I am originally from Boston, just relocated onto the West Coast now. So I'm working from Sunnyvale over there. And then I will hand it over to my co-speaker. Hey everyone, I'm Akanksha Duggal. I'm also a data scientist in the Emerging Technologies Group in the Office of the CTO. I'm based off in Boston and been working with Red Hat for almost like 2.5 years now. So let's give you an overview of what you all are going to learn in this presentation. So starting with, we will introduce you to the project that we've been working on called AI for CI. Then we'll introduce you to Operate First Community Cloud. Moving forward, we'll also share what kind of open operations data is available to us and how we are using it in this project. Further, we'll narrow it down to one famous data source, that is TestGrid, and further introduce you to the machine learning service that we will be demoing today called Optimal Stopping Point. And finally, we'll have a demo where we are going to show you the visualization dashboard, the architecture diagram, and also demo the model that we've created. So what is AI for CI?
So as you all know, AI ops is the thing of the hour. Everyone's doing it, but what does it actually mean? So it is basically AI, artificial intelligence, applied to support IT operations. And we further use these AI ops capabilities to support CI/CD processes. And hence, we have created this tool called AI for CI that uses a lot of open data sources and creates a collection of intelligent tools and applications that help us analyze and better facilitate the CI/CD data. And we have developed this project on a cloud called Operate First Community Cloud. So let's see what this cloud does. So it's precisely an initiative that's centered around open sourcing operations of software. It provides a real production cloud environment, which can be used to operate softwares and applications openly. This also provides us, data scientists, with a real platform with instances of cloud services and applications that support data science work streams like Jupyter Lab, S3 storage, database engine Trino, visualization dashboard like Superset, Selden operator for machine learning models, and many more. So open operations data, like there's a lot of data that is being created by various sources, but most of it is not usually open source. So our aim with this project is to also build an open operations data community, utilize the open data sources, and come up with a better solution to speed up the CI/CD processes. So few data sources that we are looking into are as follows. So starting with the workflow, like every time a contributor has to add a pull request, they go to GitHub. And every time a pull request is added, it's subject to a bunch of tests and builds, for which comes Prow, which is a CI/CD system that helps you put all the logs in one place, and you can go ahead and look into all those logs. And finally, for the results of these tests and builds, there is TestGrid, which is a visualization platform originally created by Google, but has the test results of tons of tests. Even though it's very visually friendly, it's often hard to understand why is a particular test failing, and then you have to go to Prow to see the logs, and it gets kind of tedious, and that's where we come in picture. So for facilitating all these processes, we have downloaded all these data sets, went through it, did some initial exploratory data analysis, then calculated some KPIs and metrics. Finally, we figured like there are few particular use cases that need more attention, and hence we've come up with AI and machine learning models, one of which we are demoing today. It's called Optimal Stopping Point. So Hema's gonna go over that. Over to you, Hema.
Thank you, Akanksha. So now that we sort of heard about what are the different data sources that we're looking at, let's actually dive into some of the models that we've been developing as part of this project. And the service that we are talking today is the optimal stopping point model. And in this model, like we just went over, we have multiple tests and multiple builds, which take a lot of time to execute. And what we aim to achieve here is we want to sort of save all of the resources so that we can predict an optimal stopping point in time when that test is actually being subjected to all those checks, and actually help save the resources as well as the time taken for the developers and for the managers who are looking at these production pipelines closely. So what exactly will this optimal stopping point try to predict here is it's trying to tell us the point in time after which the test is likely to fail. So oftentimes you have a lot of tests and builds where inside of test grid, it also comes with a status label. So it can be passing, it can be failing, it can be a flaky test, and so on. So we're mainly looking at the different passing and failing type of tests here, and we try to filter those tests. And inside of test grid, every test has a timestamp associated with it. So it'll probably tell you for today, these were all the tests and jobs that we're running. and this is the status of that particular test, and so on. So once we sort of get all of that information out of test grid and we help determine that optimal stopping point for a particular test, we can better predict and better allocate these resources so that it's not causing a bottleneck in your CI/CD process, and you can free up that time and free up that resources for maybe assigning it to some other heavier workload that's probably waiting on this particular job to complete. So that's the aim of the model. And here also we see that all of the data now is also sort of residing in inside of GitHub as well. So most of your code changes would happen via a pull request, wherein the pull request that you submit, you will have some other developers to review your code. But apart from that, there are some gateway checks that also happens where you have some automated bots who look into the repo and looking for basic information inside the repository so that it knows it can successfully move on to actually have it being reviewed further. And again, the aim was to basically help determine that point in time so that beyond which we can completely stop making those checks and those tests can just completely be reviewed further on as to why it's been taking that long to run. So what exactly is our approach here? We first, of course, start looking at the test grid data that Akanksha told us about. And since it's sort of open sourced, it's a dashboard which exists where we can actually extract all of the JSONs from the dashboard so that you can view your results in an easier fashion for data scientists to manipulate. And once we've started collecting this sort of test versus timestamp kind of a data set, we need to move on to the feature engineering of this. So now that we know what's the aim of our model, we have to actually dive into looking at that data a little bit more closely. And that's where the KPIs that Akanksha mentioned comes into picture as well. So we try to define some key performance indicator metrics out of the test grid data that we collected. And some examples of these metrics could be what's the average test duration runtime, what is the mean time to failure, what is the percentage of passing tests versus failing tests. So these are some basic KPI metrics that you could calculate, which can further help you build those features that you would actually need to develop your machine learning model. And in this feature engineering approach, we actually try to find the statistical distribution type of your passing and your failing tests. So maybe in your high school math, you might have heard of certain distributions like normal distribution, a Gaussian distribution, and so on. So this is exactly what we're doing here as well. Based on the timestamps and the test duration values that you have, we try to fit a distribution for these values. And we try to compare the distributions for passing versus failing so that we can find out that probability in time where a test is likely to fail, which is essentially what our optimal stopping point is. And once we sort of figure out that distribution and figure out that probability of failure is greater than the probability of passing, we define that particular point in time as our optimal stopping point. And you get these points by plotting something we call as probability density plots. So the area under the curve of these density plots usually give you the probability values of these various tests across the durations that they also have been running. So we try to compare both the passing and failing, since we want to predict that this test is likely to fail, and hence you need to stop your test runtime. So hence we find that intersection point. And once we've made this prediction, the most important part is to have it deployed somewhere so that you can interact with this model and make it available to other folks who are interested to use it. So we use something called as Selden here. And Selden is another MLOps platform where you can sort of use it as a model deployment integration so that you can interact with your models through like an HTTP endpoint so that you can pass all your predictions out to that endpoint, and then you can make requests to it so that you can actually interact and see what your predictions are like. So essentially, we would pass as an input to the model a given test, and then it would output the test timestamp or duration value of where it's likely to fail. And that would also get pushed into the Selden endpoint so that when you can query it in an inference notebook that Akanksha is going to show, you will be able to fetch what that optimal stopping point value is exactly. So now that we kind of know the workflow, I will just quickly go over the dashboard that we've developed to look into some of the metrics that we have. And then Akanksha will take it over to show some of the model development pieces. So for the dashboard, so this is our Superset dashboard. Superset is an open source visualization tool, which is very similar, you can say kind of equivalent to Tableau, but a little more less complicated compared to Tableau. It's quite straightforward in the sense that it's supported and backed by SQL engines. So we have Postgres SQL databases connected to Superset, and most of the data sort of aggregated into tables, and all of our data is also stored inside of this. And we try to create a simple overview of the different type of um, tests and grids, and that test grid has made available for us. And we have various filters where you can sort of see what are the different tabs. Here we've selected a particular grid, and then you can also filter for different type of tests that is being performed under a particular job. And once you sort of filter in on some test of your interest, you can look at some of the metrics here. So things like how many number of tests do we have under this particular job? What is the percent of tests passing versus tests failing? And then we also try to look at some metrics here where we're trying to see what are the percentage of tests that were fixed over time. So sometimes a test might be failing in like a previous run, and then it might get fixed in the next run. So you want to sort of capture those instances in time so that you can see what exactly is happening inside the build to make sure why that failing test ended up passing in the next run. So we try to look at some of those metrics. And then here we're looking at what was the average test duration time taken for a particular test. And these are across multiple runs and across multiple tests. What is the average test duration looking like? And this is the distribution that I was talking about. So for all the passing tests and for all the failing tests, we try to look at the test duration values, and we try to plot these distribution graphs. And we pick the top two distributions based on the betterment of fit, and we try to identify what type of distribution it is. So here, maybe it's a Pearson distribution. And then we do the same process for the failure type of tests as well. And we look at the histogram plots, the density plots, as I was mentioning earlier. And then here comes the optimal stopping point. So once we train the model against these distribution types that we've identified, we look for that intersection point here between your failing, which was the blue line, and then between the passing, which is the orange line here. So this point in time is roughly pointing to, I think, around 72 seconds. So basically, it's saying that beyond this, it has a higher chance or higher probability of being a failure in time. So that's the optimal stopping point that we're predicting. And now I'll hand it over to Akanksha to show some of the models that we've developed.
All right, coming back. Okay, I lost the cursor. All right. I'll quickly give you a brief overview about the architecture diagram to. So we start by first collecting the open operations data from various sources like tested, GitHub, Crow, that come from the Kubernetes testing infrastructure. Then we move forward to collecting the data programmatically to access it via Jupyter Hub, which is a tool used by data scientists to create interactive Jupyter notebooks. And that's how we interact with the data, save it to Ceph S3 storage, and further come up with various metrics that we want to analyze. And then once we have everything in place, we come up with AI and machine learning techniques to improve the CI/CD workflow. Um, then we move forward to the data visualization part. After the calculation, we move the data to the SQL Trino engine where it goes to superset, and that's where we do the visualizations that you just saw. Finally, we do the model development using Jupyter Notebooks, and for the deployment part of it, we use Selden, which is on Red Hat OpenShift. And finally, this entire workflow is automated using Kubeflow and Elira pipelines. And now I'll do a quick demo of the model notebook. All right. So we've written some helper functions. Okay. All right. Cool. So we develop a model called optimal stopping point. We start by getting the data from Ceph storage. Then we fetch all the tests that are available to us. And then we look into various distributions. I think there's a network issue. So we filter the tests that we are looking for, and we further fit the distribution, as Hema mentioned, according to various probability distribution functions that are available to us. So we try almost 10 of them here, and whichever has the best p-value, we use that. And finally, do the optimal stopping point calculation. So I'm going to show the model inference notebook now, as we are running very short on time. Yeah, I'm going to go to the reference side. This is the repo, right? All right. All right. So for the model inference bit, we have deployed a model on Selden, and this is the endpoint URL that we are to interact with. So Selden understands the data in a certain format, so we send a JSON data payload to interact with the model. So we send a test name and a timestamp for which we want to know how the test performed, and then we query with this base URL. And finally, the response 200 means that the service is up and running, and the result that we get is in the form of seconds, that this particular test of operator or run something something, this is gonna probably fail after 104 seconds. If it's taking longer than that, then you should probably stop your test right now and better allocate your resources to some other important job that you might have to run. So that's it for the demo. If you're interested in collaborating, contributing to this project, we have a lot of documentation available, starting from Jupyter notebooks to Kubeflow pipelines and machine learning models. We also have a video playlist for anybody to come and watch. That's the QR code for our GitHub repository if you're interested in making contributions. And these are a few notebooks that were demoed in a very quick minute. But if you want to learn more, you can go to the GitHub repository and learn more about them. And this is the URL for Operate for Cloud. It's free for all to use. You can go ahead and deploy your own machine learning applications. And we also have a workshop that myself and my colleague Ointila had given earlier in DEF CON. So you can go check it out. There's good documentation of how you can create your own AIOps tools using Operate First. And that's about it. Thank you, everyone. If you have any questions, please go ahead.
Thank you.
Testing. Okay. Hey, everyone. Sorry, I'm a little rusty. It's been a little while since I've done this. So I'm Gordon Haff. I'm technology advocate at Red Hat. I work in our market insights group, but one of my side things is I help out with Red Hat Research, particularly Red Hat Research Quarterly. So what I'm going to talk today is a little bit about the, can you hear me? How's that? Good? Okay. First, I'm going to talk a little bit about the nature of university and industry collaboration. I won't go through my whole spiel on this today, but go some basics. Talk a little bit about Red Hat Research, which I know some of you in this room are very familiar with. And then I'm just going to give you a quick summary of some of the current research projects going on. Don't have time to dive into these in any great detail, but just to give you a flavor for what's going on. So where does invention happen? Well, invention happens in academia. This has probably been particularly true since about the middle of the last century or so, when really a lot of research started happening in many kind of great research institutions like this one. What does that look like in academia? What is the research in academia? Well, there is clearly collaboration, but there's also historically often been a lot of silos within different disciplines at many universities. For example, the new AI Schwarzman School at MIT, for example, one of the motivations behind putting that new institution together was to bring some of the different types of AI disciplines together. So it wasn't just computer science. IP may be a consideration in academia. Large research institutions like MIT, I know, make a lot of money off of licensing various types of IP. One of the downsides in academia is the research is sometimes not rooted in real world use cases and practices. In fact, that was one of the motivations for the Red Hat Collaboratory, which I'll talk about in a couple minutes. Working in open source may be unfamiliar. I mean, open source is used a lot within universities, but actually working in open source communities may not be as familiar. And there's a lot of practices associated with that. And the fundamental output, a lot of it is fundamental research, and it's often publication is how that gets expressed. Now, corporate laboratory, on the other hand, Edison's famous lab in the upper left-hand side there, that's IBM Research in Yorktown Heights on the right, another very big research laboratory. DuPont, very big in chemistry, and then famously in the lower right, Bell Labs. So what does that look like? Well, historically, the corporate laboratory has been mostly limited to dominant firms. In the case of Bell Labs, the parent basically had a government monopoly on phone service. And that really allowed them to make investments in fundamental research that might not have near-term returns. Pretty secretive by and large, fairly limited scope for collaboration outside the organization. These are for-profit companies. They want to profit for their IP. And they're often rooted in commercially interesting technology. In fact, what we've seen over time is that a lot of these research labs and dominant firms, like at Digital Equipment, for example, west of here, the digital research start to look a lot like digital product development as opposed to the longer horizon types of things. And the outputs, working artifacts, things that actually work, whether it's software, or hardware, or devices, or chemicals, and patents. I mean, IBM, most notably, every year, comes out with how many patents they had as sort of an attempt to signal how innovative they are. And then we have open source. A lot of innovation happens by knowledge diffusion in various forms. And certainly open source is a great example of that. IP concerns are mostly handled in open source, and there can be things like patents, and certainly you have to respect licensing agreement, what the licenses of the software look like, and so forth. But it is mostly handled. Successful open source projects are not just about viewing code; they're very collaborative. There certainly are single-person open source projects, but those aren't things like Linux and Kubernetes that are very well known. Now, most of the open source wins have been in software. There are certainly examples of collaborative knowledge aggregation like Wikipedia. There is RISC-V is a really interesting open spec for processor hardware, but mostly it's in software. The open source development process tends towards the incremental a lot of time, and the output is for the most part code. You might hope the output was also more documentation and things like that, but that's not always the case. So how do you go from this to organize deliberate invention using open source principles? There's a couple of people sitting in the second row who were very involved in doing this. And one of the results was the Red Hat Collaboratory at Boston University. Started 2018, jointly by Red Hat and BU. The goal was to advance research in emerging technologies in areas that both organizations were interested in. I think it's fair to say there's been expansion in the type of research that's been involved in our collaboration since then, but it started out mostly in the infrastructure space. It sponsors research projects with BU faculty and Red Hat engineers, and obviously the students of those faculty members. Support fellowship and internship programs, organize joint talks and workshops, engage with our BU programs and offices, and engage with the Red Hat CTO office and engineering. A little bit more about Red Hat research today. The centers of our collaboration is Western Boston area, some other schools in Massachusetts as well, Brno in the Czech Republic, and Tel Aviv. There are a number of other universities around the world involved too, but this is sort of the center of the activity. One of the reasons is one of the things we've found as time has gone on is you really want to have a strong local presence and project management and the like. If you just go, pick any university around the world and let's see how it goes, that does not work as well. We publish a quarterly magazine. The information on subscribing for free, either print or digital, is going to be at the end of this presentation, and I encourage you to do so. It's a very nice magazine, if I do say so myself. And one of your BU professors up there from our last issue. Actually, I think it's the second to last issue. I think the last issue literally just published like this week or something like that. What we do, produce prototypes, demos, jointly authored research papers, as well as code. And our focus being Red Hat is on things that are open source related. So, we're not looking to create proprietary software, for example. Internships, mentorships. We have Red Hat engineers who teach classes. We have research days events. Some of these are virtual. They've been virtual for the last couple of years, although we're going to have an in-person one in Brno next month. There's also research interest groups, and there's a North American research interest group. Encourage folks here to participate if you are interested. And basically, we coordinate participating in research proposals and international programs and so forth. They're very interesting. It costs nothing, no obligation. Check one out. And again, the information will be at the end here. So I'm going to briefly go through a few of the current projects. First is machine learning for cloud ops. This is actually the work with the BU professor who was on the previous slide. Basically, the problem here is that the diversity of components and the speed of development of software architectures, hardware architectures, make it difficult to identify, localize, and fix problems related to all kinds of things manually. In fact, it's interesting. I'm in the middle of doing some research on cloud services and been talking to practitioners about, kind of what are their big challenges. And I think like 2 of them in the last 2 weeks have said it's so hard to optimize things. It takes so much time. It's so complicated. And that is like the biggest thing. If someone could solve that for me, it would be wonderful. And we agree. Your existing approaches, just aren't fast enough to keep up with modern CI/CD processes. They're fragile, they're costly, they're not very scalable. So this is just an illustration of the work that is going on at BU in the area of ML cloud ops or AI ops or whatever you want to call it. And we've been very involved in this from the Red Hat side as well. So, you basically have applications, platform layers, underlying architecture. They're all feeding various metrics into they're being aggregated, going into an analytics engine. It puts out a unified API. And then there's a bunch of open source tooling ending up with Thoth, which is pipelines for OpenShift, Kubernetes-based OpenShift. And this is kind of some of the work that is going on in this area. Another area is Rust memory safety. I assume most of you here at least have some familiarity with Rust programming language. Basically, the idea is we've historically used C, C++ as a systems programming language. And C is, to put it charitably, not very memory safe. You have to be careful what you're doing with pointers and how you allocate and deallocate memory, or it's very easy, to crash it for one thing, but also to open up security holes because people can see memory contents that they're not supposed to be able to see. So Rust was designed to be a low-level programming language, but that sort of from the ground up had significant memory safety guarantees. So there's a project going on at Columbia that is working further on Rust, because Rust is memory safe for the most part, but it has an unsafe keyword which suspends some of the compiler safety checks within a particular code block. Well, why would you take a memory safe language and make it less safe? Well, there are the way the Rust language site puts it is, well, sometimes you won't give Rust superpowers. You want to call an unsafe function. You want to dereference a raw pointer. And there are a couple other reasons as well. Unsafe doesn't get rid of all of the Rust memory safety features, but it does get rid of a lot of them. And now the developers unhook to ensure their code is memory safe. And in fact, we're seeing the number of security advisors being filed against Rust packages is going up and up and up. So this work is focused on the automated detection of vulnerabilities. And you can see what some of these memory safety errors here look like. And basically, again, this is automation using the automated tools that we've been developing for many purposes in order to have safer code. And automation is being used in code in a lot of other places as well. But I thought this was a particularly interesting example. This is another one from VU, a Linux-based unikernel. For those of you who don't know what a unikernel is, you basically have a bootable image that's user code plus additional components that provide kernel level functionality. So if you have a call that would normally be executed by the Linux kernel, for example, it's essentially this linked library that does that for you. Now, unikernels, I think if you have, I don't know exactly what the Wikipedia article says, but if you kind of look up, unikernels in some computer history, you'll probably find reference to some projects in the 1990s around that, these were the first unikernels. In fact, this is the way that operating systems were originally built. The operating system for the IBM 709 back in, I think, 1959 or so, which is almost as old as I am. But basically first of all, it was written by some IBM customers and basically modified over the years. So really, this is how the original back-oriented mainframes work. The advantages is, well, you don't have a whole operating system kernel. You're linking in the pieces of the kernel that you need. So it's very lightweight. There's potential performance and security advantages. This has been tried a bunch of times. The problem is usually what happens is a specialized operating system gets built or an existing operating system is forked, and after time, people lose interest and it basically kind of goes away. So some engineers and faculty thought, well, what if we did something fairly simple, relatively simple, none of this stuff is simple, based off Linux. So run as a single process, run everything as rings at ring 0. So normally Linux is ring 0 for kernel, ring 3 for user processes. But run everything at ring 0, then you don't have to do those ring transitions. It also turns out this is actually rather complicated to do, because when you do ring transitions, normally in Linux, a bunch of stuff gets done in background. And so various things have had to be done in order to essentially do those ring transition tasks within a unikernel. It's, as things stand right now, it's pretty small changes, about 1,500 lines of code, and the eventual goal here, and we'll see how we get there. But the goal here is that you just make this unikernel and other build target for Linux. The Linux already supports a bunch of other build targets, so the goal would be to do this with unikernels. And there has been some promising early work. The Redis database benchmark about 33% performance over the Linux baseline. So this is sort of interesting. And finally, in a project going on at Notre Dame and Loyola on image provenance analysis. Now, I think probably most of you are very familiar that there's a lot of altered images being used out there to kind of spread untrue information. A lot of it is malicious in nature. And there's no real current turnkey solutions to this. I mean, there's various stuff out there, but none of it's really very turnkey. Fully synthetic images are easier to detect today, but they're getting better too. So that's maybe a concern down the road. And basically, determining how images have been tampered and remixed is essentially a graph construction problem. You know, what has been the progression of this image over time based on comparing various other imagery that's out there? So the primary focus of this research is to find related images from specific data sets, and that's sort of how the initial work's been done, or the internet more broadly. And as you can see, you're looking at parts of images, clusters are being created. Oh, this sort of subset of this image looks to be the same thing as this subset of an other image out on the internet, and move on in this way. This in the upper left gives you an example where President Putin has been basically a picture has been dropped into a bunch of statesmen at the internet, and it looks like they're all basically kowtowing to Putin in this photo, which didn't happen. They're also looking at some other techniques like metadata and other things. One of the outcomes of this so far has been the Upstream Pi IFD project. By the way, these slides are all on this event, and you can download them and find out a lot more about these projects. So, close out. I'd encourage you, we have additional virtual Red Hat research events, or back to physical around here. Come to one of them. Sign up for the research quarterly. Really, it's very pretty, very nice, really interesting. I think if you're at all interested in the subject of this talk, you will really like it. And join a research interest group. So with that, thank you very much. Okay, thank you. Again, as I say, slides are all online, so all the links and so forth are there, and give them a try.
No? I flipped it. Okay. It's got a boot? Okay. Well, once it's booted, we'll get started. I feel like I can hear myself now. Okay, yeah, this is great. Awesome. Thank you, Sally. All right, so it's 3, and we have all come to answer the question, IPFS, what is it and why you should care? By the end of this talk, you guys will all learn about what IPFS is, why it's useful, and what it can do for you. So my name is, I'm an associate software engineer on the platforms team under Harrison. We work in emerging technologies, and we basically look at what's new and what is important and try to find how it can fit and help other people. So what is IPFS? Well, IPFS stands for Planetary File System. It's basically, it's a storage system. It's content addressed, it's peer-to-peer, so it's decentralized, and it's linkable. And these 3 things are very important because they allow you to have a very flexible way of storing things, but also a very robust and very powerful way. So let's talk about this first point, content addressed. So when we talk about addressing schemes, there are 2 primary ones. There are location-based. So this is like when you're using a URL bar and you go to google.com, that resolves to an actual IP address. And then that IP address has to be bound to a server running somewhere. So your browser basically says, go to this IP address and then show me what is at that IP address. It doesn't really care what that content is. It just wants to show it to you. And it expects it to be something that your browser can render. And the other big one is content-based. So when you're content addressing, you are looking for pieces of content that match a given hash digest usually. So some examples of this are like, if you are pulling a container image, there's going to be a hash associated with that. And you're saying, well, I want the container image that matches this hash. So let's look at some examples and see where these 2 work well and where they maybe don't work as well. So we went through this, but if you're location addressing, you're just addressing a point in space, and that location is constant, but the underlying content may not be. If you're addressing by content, then the content is constant, but where it's stored may not be. So if you're addressing a book, if you go to a library, so let's say you want to check out the Odyssey, right? So you'll go to the library and they'll tell you, oh yeah, you can find it in the nonfiction section in the adult area on shelf 4. And that's great because it's very humanly readable, but where it falls is if you actually go there and someone moved it, maybe a librarian or someone put it back in shelf 5, you're going to be searching shelf 4, you're not going to find it. Whereas if you are addressing it by the ISBN number, that is universal. So you can go to any library and ask them for this ISBN number, or you can go to a friend, you can look at their book, and you can see that that ISBN number matches. So you know that it is actually the Odyssey, even if the cover is different. If you're addressing a building, this is the Red Hat Boston office, and a location address is perfect because it literally maps to a map. So you can just say 308th Street, Boston, Massachusetts, and you're going to go there, and you're going to be able to find this building. Now, addressing that based on its content is going to be a little bit more awkward because that maybe you could look at a blueprint and say, show me the building that matches this blueprint, or maybe you could describe it and say, yeah, it's the brown brick building. That might not be as helpful. Then if you're talking about OCI images, you can have a repository, which a tag, and you're saying like, give me the image that is at that latest tag. And that's really convenient. But if you want a specific build of an image, you're going to address it by that hash. And you're going to say, I want this hash. And I don't care what tag it is. It's going to be this exact hash. And that works really well if you want something really specific. So IPFS is content addressed. And data is located with these things called content IDs, or CIDs for short. And basically, they are the root node of a directed acyclic graph, also known as a DAG, and it's a Merkle tree. So it's basically this binary tree that you build from different hashes, and the root node of it will change if any of the children change, but you can also that's within it. You can do a ton of crazy stuff. So you can embed like smaller Merkle trees into larger Merkle trees and keep building on them. And if you want to download only one of them, then you just have to reference that content ID. So the way that we have done like resource traditionally through HTTP tends to be that you have that server, and then that points to some IP address, and then you have a relative path, which points to a file at that relative path on that server. So if you go to like google.com and you want corgi.png, well, maybe google.com always .com, but it might resolve to a different server, and all of a sudden corgi.png becomes malware.js. Or maybe someone renames malware.js and overwrites it with corgi.png. So that is one of the pitfalls, but it's really convenient. Now, when you talk about IPFS resource address, you're going to say, I want this content ID, and then you can do relative paths with that as well, and say, I want corgi.png. And that content ID is never going to change, but neither is the value of corgi.png because it's based on that content ID. So when you're talking about adding data to IPFS, there's a CLI, the prominent one that they use to demonstrate stuff is called Kubo. You would just run IPFS add, and it would take this beautiful corgi here, and it would translate that into a bunch of different blocks, and then it would build up this Merkle tree, and then finally spit out this content ID, which basically embeds a bunch of information that we'll see in a moment. And then if you want to retrieve it, you would go to your CLI, and you would say, let's get this content ID. And then it would ask the network and say, hey, like, does anyone know who has this content ID? And if the peers would talk to each other, they would look at the records, and then eventually they'd be able to say, oh, yeah, I have corgi.png, so let me save that. And then if you actually look at the anatomy, I think this is going to be too small for you guys to see it in the back here, but basically you have these children nodes, and these are going to be like blocks. So I think here it's about 256 kilobytes. It's not really important, but they basically come together to form this content ID, which is the root one. And you can download all of these individually, or you can download just the root node. So that's really important. So then folders can be made from files. So if you put a bunch of content IDs together, you can get a bigger folder. And you would just, if you want to download all the corgis, you would just get that root content ID. Or maybe if you want this one, then you would just get this content ID. And then the other benefit is that data can be linked. So they have this thing called IPLD, which stands for interplanetary data, and you can build data structures. So the file system would be a type of data structure, and then also you could have a blog, and maybe the blog has like some pieces of content. So it would resolve to that corgis with hat image, and then it would also resolve to someone's user profile. And then you would just build these bigger and bigger trees. And the really nice thing about this is that you can download any of these content IDs. So IPFS uses something called the distributed hash table, which stands for DHT. Basically, every peer in the network stores some record about where things can be found. And there's three main types of records. We're not going to go into the specifics, but basically, when you ask IPFS and you ask the network for a piece of content, they are going to find that, and then eventually you get a result back saying, oh, well, I can't find it anywhere, or maybe you do find someone, and then you have to download it again. So it's like a way to navigate the network, and we'll see how that works in a bit. Oh, yeah, it's this slide. So here's a simulation of how content propagates. So we'll say that Jackie here has this corgi, and the content ID, if you can't see it, is just U14BX. And then let's say Jackie announces that she has a content ID, so she adds it to IPFS, and then she tells Ivan, I have content ID. Ivan says, okay. And then Kevin wants to download it, so he asks, who has this content ID? And then Ivan tells Kevin, Jackie has it. So he asks again, where can I find Jackie? So Ivan tries to find Jackie in the network, and he already has her record. So he says, well, she's at 568. So he goes out and talks to Jackie and says, well, I would like to download this content ID. So he asks for the blocks, and then Jackie's like, okay, well, here are all the blocks for this corgi. And then now that he downloads it, he is able to tell both Kevin and Jackie that he has that corgi. So if anyone asks later who has this corgi, both Jackie and Kevin will resolve to it. So later we see Laura ask, oh, does anyone have this corgi? Maybe she saw it on a meme page and wants to download it. So Ivan says, oh, well, actually, both Jackie and Kevin have it. So the benefit of this much deduplication and this much content propagation is that you can do concurrent downloads because everything is split up into that block. So you can say, okay, Kevin, I only want blocks 1 through 7, and then Jackie, I want blocks 2, 4, and 6. And then they both get different blocks, but that comes together to form the same corgi. And now Laura is able to tell Jackie, Ivan, and Kevin that she also has the corgi. So as it gets more popular, you get more benefit. And this applies really well if you have some really popular container image like Alpine. We're not going to get too much into that, though. So the other neat thing is that IPFS will always tell you that the image is the same, even if they're 2 different images on 2 different servers. If the underlying content is the same, then it'll still be found in the network. So some benefits, we talked about this, but you don't need to rely on a specific location. So maybe an image was on Google at first, now it's on some other site. Regardless of where it is, it's just going to be found. You can also verify that you actually have that content because you are able to simply hash all of the blocks once you get them, and you'll know immediately, I'm being duped. This isn't what I asked for. And then deduplication, of course. So if you are downloading these blocks, because everything is block-based, and then, so let's say you go to a really large website, right? Something that has a lot of CSS files, and then you have to download all of those. And then you go to a different website which shares some of those CSS files. You would only need to download the new ones because it would be able to say, oh, well, I actually have these other ones that I downloaded earlier. So it has caching involved too, which is nice. And then we talked about downloads increasing availability and data being immutable. Otherwise, you're going to know because the content ID is going to change. So there's also something called IPNFs, and this uses a public key infrastructure to basically, like, if you want to have content always resolve to some content ID, and then you want to change the content later, the problem is that the content ID is going to change. But if you don't want to constantly give someone an updated content ID every time you push an update to your website, what you can do is you can create a signature of some content ID that you always wanted to resolve to, and then you talk to your peers and say, hey, I want my ID to resolve to this value. Here's the signature. So here's that process. So here Jackie wants to always resolve to, she wants to pin that corgi to being her resolution. So she'll sign it with her private key, and then it creates a signature, and then she'll say, okay, well, oh yeah, this is also important. So the ID is a hash of the public key. So she can then talk to Kevin and Ivan and say, hey, I want my ID to always resolve to this. Here is my signature. And then they will store the content ID they want it to resolve to and the signature. And then, so now Juan asks Kevin, okay, what does her ID resolve to? And then Kevin says, oh, it resolves to this. Here's the signed record for it. And then he's like, okay, well, where can I find U14BX? And then he says, again, Jackie has U14BX. And then Juan simply has to talk to Jackie and download it, or whoever has U14BX. And now, again, he downloads it and he announces it to the network. There's also this thing called PubSub, which we're not going to get too into, but it's like, it's a way of publishing and subscribing to messages that are on the network. And this is really great because you can do conflict-free resolution, conflict-free replication data types. These are largely used in distributed systems. There's a data that is already built on this called OrbitDB. It's a key value database, but you basically plug in some information and all of a sudden you have this database that can sync a bunch of values with other databases and allows for more client-side applications without the need of a central server. which is nice. So use cases, distributing packages or containers. This is really nice because, again, if you have a really widely used container image, it's going to be deduplicated. Linked data, because this doesn't rely on any central server, and because you can build data structures, you can just plug this into something like a Git commit or on some blockchain transaction, and it's always going to be there. Edge data is also really useful because as content becomes more widely available within the network, because more people have downloaded it, someone in Antarctica doesn't have to reach out all the way back to a server in North America to be able to download it. They can simply leverage the concurrency to download it from multiple peers. And then static applications have a personal website. You could just put that on there. Serverless, you can never talk to a server and then be able to still get that benefit. And then information archival, this is really great because you just know that it's going to be that information, and then you could just pin it on IPFS. And then large data sets, this is the other really big one. You can put up a bunch of data and host it on IPFS, and because you have that deduplication inherently, if you later change something in that data set or you add something to it, you don't have to republish an entirely new data set, and people downloading it only need to download the changes. So that is a huge benefit. Okay, so it's demo time. If you guys want to follow along, you can quickly see the barcode. I'm going to take a sip of water because I am thirsty. So we have 4 demos. I don't know how much we are in time. Oh, we're good. We have about 13 minutes left, so that's awesome. All right. See a few phones, so I'm going to keep it up for just a second longer. All right, we're good to go. So the first one we're going to talk about is website deduplication. And I mentioned this a bit earlier, but basically, so let's go into, where am I in the world? Okay, into Ipfs Web App Demo. So I have here a Node app that I put together. So I'm going to do npm run build. And this is just going to build it. It's a Svelte application. And then I can do Ipfs add, and we'll add that distribution directory recursively. And this adds everything to Ipfs. So now we can just copy the bottommost content ID. And what I want to do for you guys is I want to plug this into the CAD Explorer or IPLD Explorer. And this will actually show me the entire structure. Got to zoom out a bit because there's a diagram here, but it shows me the main nodes that I have here. So we have an assets directory, and we have an index.html. So if we go into assets, we'll see that there are a few more things. We can note the content IDs in here, but I'm just going to create a new tab because what we're going to do is we are going to do, let me actually show you the website before I do anything else. So I think it's npm run dev. Yeah, there we go. So let's open this up. So this is the website. We can also access it through the IPFS gateway. I believe we can just copy that content ID from here. And if you guys are following along, you can just do this on your laptops because the content ID is the same. But here we have the website, and this is accessing a gateway through the ipfs.io domain. And it's rendering that entire web page that I just put up in a browser, which is hosted on my laptop. So now what we can do is I'm going to exit out of that. I'm going to switch to a different build where I have edited it. And I'm going to do the same thing. I'm going to do npm run build. And then I'm going to just re-add that. So this gives me a different content ID. And now we can access that through the gateway again. And now I've added this Vite plus Svelte plus IPFS. And this is a complete web page, which is statically hosted. It's entirely client side. And then I can get that content ID and I can put that into the Explorer. And this is going to show me a similar tree view. But then if we go to actually compare the two, this is really small for you guys. We'll see that the assets directory ends in gap. Then we can look at what the assets directory ends in here. So it's SPV or XPV. So it's changed. But if we look at index.html, that ends in 6pk. And here it ends in L86, which makes sense because I changed the index.html. But if we go into assets, we can look at these four things, and then we'll go into assets in here. And we'll see that there is some overlap. So we have an extra file in here, and it looks like the CSS file didn't change, which is awesome. So we didn't need to re-download that. And then that index file, so YG. So that index JavaScript did change. That svelte file, 1F, that didn't change either. And then that byte file, that didn't change either. But we did get this new IPFS SVG, which is what we added. So that's how deduplication works with IPFS. It's really great because imagine this, but on a much larger website with a lot more assets, you're going to do a lot less downloading. So that is what I had for the first demo. So we'll talk about content. So this benefit. So for this, I have two EC2 instances which I've created. So IPFS node 1 and IPFS node 2. And what I'm going to do is I am going to create a, what did I tell myself I was going to do? Oh, yeah. So we can do echo hello devconf Boston 22, and then we can do that date. So we'll say date. I'll just do date. And then we can pipe that into IPFS add. So this adds that string into IPFS. You can try viewing it from the gateway. Maybe it'll be nice to us. Sometimes it's a little bit slower because it is a decentralized network. And if you only have one node running it, oh, this is the wrong tab. So we'll want to go into ipfs.io/IPFS. Oh, yeah. So this is displayed directly in the IPFS gateway. So we see hello devconf Boston, and it says the date. So 23. Cool. So what I can do from my host is I can say IPFS. So I can query the DHT, and I can find anyone who has that content ID. So I'll do find probs, and that one shows up. So that must be the EC2 instance. We can get the value of our ID here by just running IPFS ID. There's a lot of, I had to make it really large. So yeah, so this ends in DNM. So that is this instance. So that's the only one who has it. But now if we go to the other instance and we'll try to download that, we'll say IPFS get. And that'll query it and it'll download it. And then it'll re-provide that to the network. And now if we do the same exact query, let's see if this works. Yeah, so now that shows up as being a second provider, which is awesome. So that is how that works. So what's the third demo? Oh, IPN. This one's really cool. So this is the IPNS I was telling you about. So what we're going to do, I was gonna go into node 1. We're going to clear this working directory. So we're going to go into devconf demo. We're going to go into the web app. And we're going to do, so I have a build script for this. IPN run build IPNS. Basically, I guess I'll show you the regular one, how it's done. So we'll do npm run build. Again, this builds it. And then we'll add that recursively. So we'll do ipfs add recursive. And then what we'll do is we'll say ipfs name publish. And this is that deal I was telling you about. So this signs it and says, I want it to resolve to that value if you go to my ID. It's going to take some time. Not too long. Okay, there we go. That was faster than I thought. So there we published it. And now what we can do is it says this is the value published to. So we can go to ipfs.io/ipns to access the naming system. And then we can plug that hash in. Missing a DNS. Oh, I know what I did. Missing colon at the end. So now it's going to try and query the DHT. It's going to see what that resolves to. This one takes a little bit longer. I'm just thinking. So who liked the turkey crayon apple lunch today? Can I get a show of hands? Okay, 3. Caesar wrap. What was your favorite lunch today? The shrimp was underwhelming. Okay, we'll have to let the staff know. Oh, wow. So this is taking a bit. I'm not sure why it doesn't want to be favorable to me today. So while we wait for that, does anyone have any questions? Yes. Yeah. Yes. Yeah, so this is heavily inspired by BitTorrent. What they did was they improved on a lot of the faults of BitTorrent. So with BitTorrent, I believe you need some extra information to access the DHT. With this, it's more of a global network, and linking is a lot more embedded. Yes? Yeah, so that's the deduplication we talked about. So the new content ID that you get will be different because you have an edit to it. But if you look at the underlying blocks, and if it's a really big file, some of the blocks may actually be the same. If it's a really small one, then it will be entirely because it's just going to be one block. It's very similar, yeah. So it's similar to git diff. So this isn't working, or if it is, not very well. Not sure why. Did I need to do something extra? That is strange. I was testing this all night, and then earlier today. Oh, there we go. We got it. Yeah. Thank you. Okay, so this was the original page that we had. So now I have a build script for performing all the intermediaries. So we're just going to check out the with IPFS branch. Oh, it's diverged. You check out with IPFS. Oh, no, we're still on it, so that doesn't really matter. So we'll do npm run build with IPNS. And then this does the build, and then it publishes that hash into IPNS, so we don't have to do more commands. That's all we want in the end, is less commands. I guess it depends on the commands.
We're just about out of time. So
All right. This should take like 1 second. Seconds up. Okay, there we go. So now we don't have to do anything extra. We can just refresh that page. And now we see that Vite plus Velt plus IPFS. And there we go. So that was resolution through IPNS. We didn't have to do anything extra. It was the same value. There's a few other ways that you can get it to resolve, but this is a built-in way, which is, it works out of the box, which is nice. All right, we don't have time to get to the other demo, sadly. I don't think there's time for questions either. But yeah, so let's go back. Oh wait, I'm not done. So in conclusion, IPFS is awesome. And then like this slideshow, we have a next.red hat page for IPFS. You can also check out ipfs.io. You can find a lot of information there. And then my LinkedIn is there. It's just Oli-Silkin. And then we're building this thing called IPFS Cluster Operator for a large scale like data distribution method through IPFS. And yeah. So that was IPFS. All right, I will hand it back to the next people.
All right. So hopefully this adapter works. Presenter view. I don't know how this is going to get started. There's something is not plugged in. Oh, perfect. Okay. So, yes, I think we can put in this one. And to here, and we want to full screen it somehow. I'll put full screen. And do I have control of the mouse? Yeah. All right. Who is ready for an exciting presentation on Cicd Store and Rust? Yeah! All right, great. Welcome. So I am Lily Sherman, Senior Software Engineer at Red Hat.
I'm Dikshna. I'm a software engineer at Red Hat.
Can you all hear us okay? All right. Okay. Can you hear us better now? All right. I'm going to try to speak into the microphone. So that's who we are. And this little guy on the screen is Ferris. He is the mascot for the Rust language. We'll get to him a little bit later. We also want you to know that we are two humble representatives of a much wider community that works on SigStore. And we're excited to be here today to give you a bit of an overview on it and how we are starting to use Rust in the SigStore project. So open source software powers a lot of our products and technologies today and works across many different devices. And due to its advantages, including auditability, transparency, and extensibility, it's going to remain pretty foundational and inextricable from our everyday lives. At the same time, there has been more emphasis recently on improving security in the supply chain, both in proprietary software as well as open source. And there's even been a federal executive order to highlight and emphasize that we need to improve supply chain security in software. Now, as you can see in this image, the supply chain for some application can be relatively complex. This is because applications are not written in a vacuum. So the supply chain for some application will include things like that code's dependencies, the various build systems, testing systems, CI, and other artifacts that are involved in the process of bringing this application into the end product. So an attack on any one part of the supply chain is going to introduce bugs into the end result, and this is why supply chain security is going to be critical for many of the things that we do today. Now, signing an artifact like a software binary or a container image with a cryptographic private key remains the gold standard for proving the integrity and authenticity of that artifact. So the signature tells us that the source of that artifact is a specific source, hopefully a legitimate source, and also that the artifact has not been altered since the source signed off on it. Now, unfortunately, a lot of the artifacts in the software supply chain today are not being signed. And in fact, the ones that are signed are often not verified. The signature is not verified by the end user. So this means that a lot of our software and artifacts and container images actually remain vulnerable. And someone in the broader SigStore community actually did a bit of an investigation and found that there is a popular programming language, and in the package manager, the top 10,000 most downloaded packages, of those packages, about 2% were actually signed, which is a fairly low number, but that's pretty typical across the board. And some of the reasons for this low uptake in signing, even though signing is such a powerful tool, could be because key management is actually very burdensome for the signer. So if you're going to sign some kind of artifact, you are responsible for keeping track of the keys that you used for an indefinite amount of time. You have to deal with any kind of key compromise or revocation, even if you have stopped working actively on a project, if you've left a community, changed jobs, gotten new hardware, that's still your responsibility. So it can be quite burdensome. And additionally, the way that signing is done traditionally doesn't always play well with automation. So a lot of the build systems today actually rely heavily on automation, but the private keys that are used in that process can even leak onto third-party infrastructure in the worst cases. So to overcome some of these problems, SigStore aims to introduce tools and public good services in a user-friendly way into the open source ecosystem to increase the adoption of signing and improve the security of the supply chain.
So SigStore is this umbrella ecosystem, right, under the openness community. What it tries to be is it tries to be Let's Encrypt for software signing. So Let's Encrypt, for those of you who don't know, is this like awesome open source project that distributes TLS certs for free. So what Sixstore is trying to do is, it's basically the same thing. It's trying to provide like free and open source tools so that everybody can sign and verify software. So there are many moving pieces involved here, but I'll like deep dive into 3 of those components in the next few slides. But as an overview, there are like 3 main components. There's Fulcio, which is the certificate authority. There's Recore, which is the transparency log. And then there's Cosine, which signs and verifies artifacts. In terms of community adoption, there's a bunch of community adoption already. There's Arch Linux, there's Kubernetes, there's GitHub. So GitHub even encourages its users to use Sixstore for its tools and like Sixstore tools for its workflows and binaries. There's also Ruby and Gems. So basically, we have this bunch of projects that are ready to use Sixstore tools, and we're very excited to see that happen. The first component is Fulcio. So Fulcio is a certificate authority that you would go to in order to get a code signing certificate. If you've ever logged into websites like Twitter or Instagram, right, it basically defers you to this other login flow, like Google or like Facebook. Basically, these are open identity providers. What they do is they give you a token, and these platforms vouch for your identity. And Fulcio takes this token, takes your public key, attaches it, and gives you a certificate. So basically, you know who the signer is and who's vouching for that signer. We use publicly available open identity providers like Google, GitHub, Microsoft. But Fulcio is compatible with like corporate OIDC providers as well. You just have to like spin up your own instance of Fulcio. The next component is Recore. Recore is a transparency logger. So this is a immutable ledger, and you can append entries to it. Because it's based on a Merkle tree, you can actually walk the hash chain all the way back to the root and ensure that like an entry actually exists, and make sure that like nobody has tampered with any of the blocks, like cryptographically verified. When I say we like sign artifacts, we're basically signing like containers and blobs, but we're not storing the contents of these containers or blobs. We're only storing the digest, the signature, and the code signing certificate. But there are 2 exceptions to this. One is a provenance attestation. Basically, it gets information about like how the image was built. And 2, timestamps. So Recore is also a timestamping authority. So every time you get a timestamp, the entire object is stored in the log. One thing to note is that Recore performs signature verification every time an entry is made into the log. So if you make an entry into the log, you can be assured that the signature was valid at that point of time. We also have like a team in Purdue University that makes a monitor and makes sure that the logs are cryptographically verified and make sure that like the entries exist. The third component is Cosine. So Cosine is a client that Sixstore uses to sign containers and blobs and verify those signed containers and blobs. So how it does it is it generates a private and public key pair using the key generation mechanism that Sixstore uses. It then talks to Fulcio after like it goes through the login process of like the open identity providers. And then it takes the certificate, uses that certificate, the private key, and the artifact, and generates a signature. You can then upload the signature, the public key to the registry. And finally, it makes an API call to Recore to upload the signed container. This slide is basically, it tells you how all of these 3 components like work together. This is one way in which you can do this. You can use like Sixstore tools in like different ways. So in this slide, you basically generate a short-term, shortly existing key pair, and then you authenticate using an open identity provider like Google or GitHub. And if you successfully verify it, it provides you with a code signing certificate, which is then later published to the transparency log, which is Recore. The user then uses the generated key pair and the signed certificate to sign the artifact. The signature is also uploaded to the log, and then the signed artifact can be like published to the registry. At this point, when you're done with the signing process, you can discard all the keys that you've generated at this point.
All right, so that's some information on Sixstore. We're going to now take a brief detour to talk about Ferris's favorite topic, This is the Rust programming language, which is a project that aims to increase security in source code and therefore indirectly also increase security in the supply chain as well. Traditionally, there was kind of an unfortunate choice between programming languages that are highly performant and therefore appropriate for systems programming and embedded devices like C, and on the other hand, other languages that maybe have more memory safety mechanisms built in with stuff like garbage collection, but are not necessarily performant. So Rust is bringing together the best of those two different worlds. It's becoming a very popular program, especially for systems programming for those reasons. It's got the built-in memory safety, type checking at compile time, very good performance, relatively small footprint. And so for these reasons, many security conscious projects out there today are written in Rust or are using Rust in some manner. And we thought that it would be a good idea to make it easier for those projects to also integrate with Sigstore. So this is where we introduce Sigstore RS, which is the Rust-based subproject of Sigstore. Now, before you start to worry, the original Sigstore is still there. It is not being replaced. It is actually thriving. So the intention here is not to replace anything with Rust, but rather just to have an extra option for people so that they can integrate with any one of these sub-projects as they see fit. And the intention is also to basically take key functionality from the original Sigstore and from the components that Judson just talked about, Fulcio, Recore, and Cosine, and to make those available in this Rust subcrate. So this has its own repo under the Sigstore umbrella. And some of the features that are available already today include verification of signatures on artifacts in a container registry. We have available the OpenID Connect flow with Fulcio, and some works in progress include key generation and signing, as well as integration with the Recore API. We have pull requests up for those, so check back soon. I think they will be included shortly. And as you can see in the image down on the right, there's actually already been a fair amount of interest in Sigstore RS based on the number of downloads of the Sigstore Rust crate. And there are already some projects that are using it. For example, KubeWarden, which is a policy engine for Kubernetes, is using Sigstore RS for its verification. Additionally, we were considering how we can best start to integrate the Sigstore Rust crate once it's a little more fully fleshed out, how we can start to integrate that potentially with the Rust language ecosystem. So this is very exploratory work, but the idea would be that during the cargo publish process, which is when you are taking your Rust package and pushing it up to the public package registry, there could be an optional keyless signing flow using Fulcio and Recore so that the crate would be signed and then the information regarding that signature and the Fulcio certificate could be pushed up to the Recore transparency log. The Recore metadata would also be embedded in some of the crates metadata. Therefore, they would be linked. And then during the cargo process of fetching the package, it would do a validation using that Recore metadata to make sure that the signature checks out. Again, this is very exploratory, but we think it could be exciting. So if you have thoughts about that or an interest in it, definitely come chat about it or hit us up on Slack. And now we will have a brief demo. Brief interlude followed by a demo. I think I can mirror the displays. I can maybe also just do it. I'm just trying to do it. All right. Are you all able to see the screen properly, or should I make the font bigger? Okay. Bigger? Okay. Is that good? Okay. All right. So what you are about to see is I have basically an image. It's an artifact that I pushed up to the GitHub container repository. Actually, I can show that briefly as well so that you have an idea of what's going on. If I can control the mouse. So this is just what that looks like in the GitHub container repository. This is the original artifact. It has a specific digest, and you will see as each signature gets pushed up into the same container repository, that same digest is basically embedded into that signature artifact as a tag. And how that works, I'll show you first with the regular cosine, and then we'll go through the verification flow with the Rust cosine, or the Rust functionality that mimics that same cosine functionality. And then we can also do a quick keyless flow to show you if you're trying to integrate with Fulcio and not manage your key pair, you can also do that. So there is a command called cosine generate key pair. You might want to enter a password for this, but for the demo, we're not going to. And what this does is it basically generates a public and private key that you see here. We can then use that same public and private key to do cosine sign on my artifact. We're going to pass in that key that we just generated, and we're going to specify the container repository, the artifact, and its tag. And you can see it's pushing the signature to that same container repository, which is where it puts it by default. Now to verify that signature, we can pass in the public key that corresponds to the private one we signed with, specify the correct artifact, and you can see the claims are validated, signatures were verified against the specified public key. So this is the cosine flow, just using keys that were generated locally on the system. Now, this is going to use the SigStore RS verification. This is our verify binary. We're going to pass in that same public key. You can ignore these parameters, and then we specify the artifact. And as you can see, the image was successfully verified. This info is just here because we weren't using Fulcio in that flow. Now, if you want to get more creative, you can use the keyless signing flow. So we're going to go ahead and remove our keys that we generated. So there's nothing there. And now we're going to use cosine without specifying a key. And we're going to have this cosine experimental flag. This is here right now. It's going to be removed, I think, shortly, because using Fulcio and Recore with cosine is still experimental for the moment. We're going to sign that same artifact, but this time I'm not specifying any type of key. And you can see in the output, it's actually generating ephemeral keys, and it's bundling that up into the Fulcio certificate. So your public key is going to be bound to your identity. And this is the OIDC flow that we mentioned earlier. So you can basically pick which service to log in with. Authentication is successful. And this is, again, pushing that signature up to the container repository once it succeeds. And now we can use the same keyless flow to do the verification with cosine. Again, we need that experimental flag. We're not passing in a public key this time. It's just going to use the Fulcio certificate that it can pull from Recore. And that's a lot of output, but if we scroll up, we can see claims are validated. The claims in the transparency log were verified, so that's Recore. And the certificates were verified against the Fulcio root. So our signature checks out 2 times. All right, so we'll go back for 1 second.
So yeah, I hope you all enjoyed our talk. These are a few of the links if you want to know more about Sixstore or like know how to use those tools. We're very active on Slack, so like if you have any questions, please do reach out, or if we're happy to like, collaborate. Now we're open to any questions that you have.
In the demo, I saw you push 2 new signatures. Will they be on that same GitHub repository that you had there before?
You can push. Let me make sure you can hear me. You can push multiple signatures, and they will all show up in that top .sig blob that you see up there. So it basically embeds the signatures as layers, I believe. And you can definitely sign multiple times with multiple keys.
So you mentioned that Sigstore is like Let's Encrypt, but for code. So if I, as an attacker for Let's Encrypt, if I want to compromise your website, I need control either over the DNS records for your site, or I need to be able to control some of the content, or have basically full content control over your site. So what do I need as an attacker to compromise a repository that's secured by Sigstore?
I think our root of trust is the email access, right? Like, so the identity, right?
For the individual. So, I mean, there are several compromises that like could still happen. This doesn't really prevent someone from stealing your private key. It just makes it more obvious if they've done so by monitoring the transparency log. Someone could also like hack into your email and be able to do the OIDC flow instead of you. That's an inherent risk. The full CO root is actually like one of the more secure parts because it uses something called TUF, which is the update framework. So there are multiple signers, and then authority is delegated according to this very well thought out process, and keys are occasionally rotated. So, I mean, I think those are the points of attack that I would think of. Does that answer your question, or do you have like a more?
Yeah, so it seems this one of the big things that's protecting us is like if I hack into GitHub and I have full control over GitHub.
That would be a problem.
Yeah.
Well, no, it wouldn't, right? Because I wouldn't be able to overwrite your code with something malicious and still have a valid signature, right?
If you're able to thwart the OIDC flow by signing in through GitHub, is that what you're talking about?
No, like if you have a nice repository and it's signed correctly, and I, as an attacker, I hack into GitHub and I want to overwrite it with something malicious, like I wouldn't be able to do that because I wouldn't be able to generate a valid signature for that, right?
So let me think. So if there are artifacts in GitHub, are you talking about the container repository?
Yes.
Yeah. So that is part of what is protected with this external signature. For example, if the signature is stored in Recore, that would be much easier to detect. Yes.
Okay, thank you.
So you mentioned that Sigstore RS is a subproject of the original Sigstore, which is written in Go. So as folks that work on that project, how do you ensure that Sigstore RS maintains all of the upstream changes that are made in the Golang project and that's kept up to date?
Still a work in progress.
Yeah, like I mean, Sigstore RS is a completely different repository, right? Like with like different set of contributors. So like we're trying our best to like see what features like Sigstore has, and then like bring it in to Sigstore RS with Rust.
Are there other similar sub-projects that are using different languages?
I think Ruby.
There are various integrations happening with things like Ruby gems, but Sigstore RS I think is special because it kind of has its own repo. So there's the Sigstore organization, and then beneath that there are things like FullCO, Recore, and then Sigstore RS is kind of like an amalgamation of like various components from the top level Sigstore. We don't have feature parity yet. I think the idea would be that they'd be basically able to do the same stuff, but I think it's more or less use case based at this point since it's a relatively new project. So if there's a feature that somebody really wants, that's going to be included sooner.
Thank you.
We actually don't have any more time for questions, but feel free to reach out to them on the Slack channel.
Thank you very much.
Thank you. Hello. Very good. Good. Thank you. Great. Good luck.
Let's see how I do. Yeah, right? Okay, can everyone hear me? Thank you. All right. So welcome to my talk, which is getting stuff done with Fedora CoreOS. I had another word for stuff, but I figured that was probably not the right word. My name is Joe. I'm a software engineer at Small Step. We do managed PKI and SSH certificate management. So if you're looking for something that makes your life easy with doing TLS certificates, you should check us out. We work on a lot of cool stuff, somewhat related to the SIG store stuff that was being talked about. I'm also a Fedora package maintainer. I've been a member of the Fedora CoreOS and Fedora Cloud special interest groups. I'm a super long time Linux user, and I work on cool stuff every day with Fedora CoreOS. So you most likely know about Fedora CoreOS if you went to Dusty's workshop or his talk with the rest of his team. I'm not really going to get into that, I'm more going to talk about how you use it and how you operationalize it. Tooling, workflows, designing butane to fit your needs for you at home or at work or for class. Really kind of focus on like real world use. If you had to take a picture of a slide, this is probably the most important slide. And I'll have the slides available, but this slide is basically tooling with links and how you would use things. And then also like design patterns, which is like templates, snippets, pre-made units with system. And I'll get into the tooling here on individual slides here and also the design patterns. So let's talk about workflow. I'm sure with like any software project or any project you're working on, you're like, well, what the heck am I going to build? Like, what does this thing need to do? So you really need to, identify what you're building. Am I building a home lab at home in my basement with HashiCorp Nomad? Am I working on something for work that's internal? Am I delivering a product to a customer? Identify that. Then write your butane, right? First step to drawing an owl, draw the head, right? Start figuring out how your system needs to run on Fedora CoreOS. Convert it to Ignition and launch it and test it. Seems pretty simple, right? And then iterate. I think every time I start a new project, the first time I try to boot my Ignition configuration, it never boots. Like there's something wrong. So you kind of have to go on this cycle of figuring out, well, what did I do wrong? How do I get my software running? How do I achieve my goal for my workload to run correctly? And then deploy it to production or your basement or for your coworker that just needs the problem fixed. And then over you probably are going to have to iterate. And the project will age. You need to do an update. Something isn't going to work. So you probably got to go back to step 2 and start all over. So, I mean, this is a no-brainer workflow. I mean, everyone does this for, software engineering or just, any project they're doing, right? Well, you need tools. And so I found myself constantly rewriting the wheel to interface with butane, okay? And it was a bash script. Well, it was a real bad bash script, and it turned into an even worse bash script. And I'm like, okay, I got to scrap this. And so I wrote BUPY. And it's basically a Python wrapper that sits on top of the butane binary. And it not only will let you interface with butane through Python, like as a Python module you can import to your Python project, but it also, like, it's a command line application that you can use on a Linux-based laptop right now. And it lets you do like conversions. It lets you do templating with Jinja 2. It'll also interface with QEMU and launch a VM on your workstation. So if you're hacking away at your butane, you can save it, run it through BUPY, and it will launch. You can use the VM command, and it will launch right there on your workstation. And you can see your work really quick if it's bad or good. Oh man, that did not turn out all right. Well, there's a YouTube video here of like a quick demo of BUPY. When the slides are available, you can watch it. It's like no big deal. Yep. Okay. A lot of people use Terraform. Honestly, like the templating stuff that was in BUPY, the first time I saw anyone doing any sort of templating came from the Poseidon project, which is DYI Kubernetes, like vanilla installer. Super great project. The Terraform modules that that project kicks out are like first class. So that's the Terraform Provider CT module that basically will let you use Terraform to consume a butane template, and it uses Golang templates. And it also has snippet support, which I'll get into. So they were the first project that allowed you to split up your butane, because if you are writing something pretty complex, I mean, if you see Kubernetes YAML, like that's not very enjoyable because it's super long and So butane can also get long. So splitting it up makes life a little bit better. Matchbox is great for like on-prem or your home lab. You can PXE boot off with Matchbox, and it will convert. With this Terraform provider, you can feed it butane templates, and then feed variables into that, and be able to rubber stamp things down. So really, I mean, I feel like honestly, templates. If you're not using templates for your infrastructure, all roads kind of lead back to them, especially doing things over and over and over again. It's a reusable rubber stamp. Gives you all the knobs. There's certain, like I built a HashiCorp Nomad cluster for work, and I use the same Jinja 2 template for the control servers, for the compute servers, and for some like ephemeral servers. And so it's just based on tagging that I'm feeding in with Pulumi. I'm able to generate a huge cluster very quickly with one template. I've done templating, obviously, with Go templating. My bash script that was the precursor to BUPY uses env subset. I put PHP Smarty templates on there because it's just really easy to make fun of PHP. I love PHP. PHP is great. It's really great. So yay templates. This is just an example of defining a server. So the configuration for Nomad will be a server or else, based on like a tag you're feeding in, a variable that you're feeding in. Templates are great. So like snippets, I think snippets are kind of like the make your life better. Templates make your life better. Snippets make them even better because you're able to separate concerns. So if you've worked in a very large organization, or even like you're just pairing with somebody, you say, well, you're an expert in writing infrastructure, this part of the server, like you're the application developer, you know how this needs to run, you own that part. So you literally create a snippet of butane, and then you can create one for the firewall that's owned by a different team, an update config that's owned by IT based on their policies, and then like an SSH config that's owned by the security team. And with Terraform, with those Terraform modules, you can kind of write snippets and they will merge them all together and then process that as one big template. And it will error out if it sees duplicate keys and stuff like that. I'm adding in snippet support to BUPY, so you'll be able to break your butane up into consumable chunks. Because I really, for me, I've written so much butane, I've written it over and over and over. Oh, where's my user's stuff? Okay, it's right here. Pull that in. So it allows you to break things up and not have to like reinvent the wheel the entire time, which speeds up your development. Pre-made systemd units. Now, this is something that I've been doing for probably the last 3 or 4 months. It's easier if I'm consuming a piece of software that has a pre-made unit. Typically, it will be on a GitHub, and butane can fetch a file. So if I see a pre-made unit sitting on a GitHub and it has a tag, it's versioned, and I'm like, okay, well, I don't think that version is going to change. So I pull that file directly from GitHub and let them worry about its configuration. And then I use like systemd overrides to consume that unit. So this is kind of an example. So Small Step has a CLI program that you can feed in with a systemd unit to like renew certs on a timer, right? And this unit right here is really generic. It has a bunch of things you can feed into it with environment variables. And then I'm pulling it down as part of my butane. So I don't really need to write this or worry about this as long as I trust where I'm pulling it from. And so I also use the hash to make sure it hasn't changed, so it has the change underneath me, breaks and things. And then I simply override it with an override in butane to configure how that unit interacts. And I'm able to kind of like let the Small Step, my coworker who owns this unit at work, I'm trusting that he's doing the testing and make sure it works, so I can just override it. Actually, on this one, I actually wrote it myself, so I'd be on it myself if I broke it. for this specific one. So that's cool, but like, give me some real world examples. That's my boss. I told him I was going to put him in the slides. His name, he's a cool dude. So, yeah, like real world examples. It's like really hard to like demo this stuff in a project. So, all I did is I have one link for like a home lab setup. If you want to run HashiCorp Nomad, you can go to that repo. It has an example butane variables file. Fill it out with like what you want, and then it has a Jinja 2 template, and you can process that and use that to boot like a bare metal or a VM with a single node HashiCorp Nomad instance. So that's pretty cool. And then at work, we had a customer that does a lot of on-prem stuff, and private Acme is kind of a new up-and-coming thing where everyone has Acme clients for getting TLS certs, but you can't really get private internal ones through Let's Encrypt, and you wouldn't want to put your own Acme server on the internet, right? Because then anyone could query it and pull a certificate. So we actually have our free like DevOps product that lets you hook in and run an RA directly inside your home lab or at work or in development, and then you get the Acme workflow for getting like TLS certs for like mutual TLS, or just like trust. If you're doing your development, you can hit something that has a real cert that your computer trusts, which makes life a little bit better. So that is a template as well. You can consume that and basically launch that, and then you should be able to hit it and pull a TLS cert off through the Acme RA workflow. So really, now you've kind of drawn the rest of the owls. Like, well, what do you do next? And like one of the biggest things that I tell not only my coworkers, but anyone, my friends that are using like Fedora CoreOS, just launch it and forget about it. Like, don't let the auto updates work, because I can count. I've been using it, I don't know, ever since they merged Atomic Hosts with CoreOS Inc. And I think I can count maybe one time where I was like, okay, that upgrade on stable didn't go great. So for the most part, you really need to figure out like what's good enough uptime. Like, I mean, if you're mission critical, you need highly available. That's going to take a little bit more engineering work, where you launch a bunch of instances, load balance over them, or you could just have just good enough uptime. Like, if you're doing a workload for a coworker, ask them a question. Does this need to be online all the time? Chances are they're going to say no. And if it does, then you can have a conversation. But, for the most part, some of the best infrastructure I've ever had is on a DigitalOcean VM that just keeps on keeping on. So, figure out what uptime you need. Try to advocate for just good enough. Don't turn off auto updates. Let them ride. You could turn them off and then have like a workflow internally where at a previous organization, we did quarterly refreshes. We would launch a bunch of servers, and just let them sit. Unless it was a major thing that we had to do something out of band, then every quarter we would basically cycle them out and relaunch them. So, and things are going to atrophy over time. And one of the advantages of using like templates is, well, you can just relaunch something that's exactly the same. Fix any problems that may have happened, drift that's happened over time. And you can see that really quickly with VUPY on your laptop, and then roll that out to production. That's the talk. Pretty quick. If you want, all these links will be available. I'm on IRC. You can hit me up on Twitter or on GitHub. And thank you. Any questions? I probably should ask that. Maybe that's an important thing. Yeah.
Yeah.
Okay. What's up?
What I was asking is, I'm curious. You mentioned the thing about updates. Could you explain? My question was, how is this technology that you discussed being used in education?
I mean, I'm not I mean, I just launched BUPY, so it's like a week old. So there's no one worrying about it except for me. I'm not entirely sure. I think there are individuals that are contributing to the Terraform stuff. That stuff's pretty stable. So I mean, I don't really, outside of just some normal maintenance, there's not much going on there for the most part. You know, when the butane spec changes, updates do roll out to that. So, any other questions?
So do you have a roadmap for BUPY?
Yeah, actually, I do. Snippet support's really important to me. I want to be able to support libvirt because QEMU is great, but like libvirt does give you a little bit more stuff under the hood. On the GitHub, I do have like a punch list. Without pulling it up, I can't remember. I wrote it down. So if you go to the main GitHub on BUPY, you can see I have like a roadmap. But if people start using it and they have good ideas, PR is welcome, or I'll do it myself. So.
I'm wondering, would you support Type 2 hypervisors like Oracle, VirtualBox, and VMware, as well as the Type 1s you mentioned?
I don't really want to write an orchestrator, to be honest. So probably the short answer is no. The reason why I wrote BUPY was to solve a problem on my workstation. I wanted to iterate extremely quickly on my terrible decisions that I'm making within butane. And the bash, everyone that I know that's working on Fedora CoreOS, I asked Dusty, well, how do you launch stuff? He goes, well, I got a bash script, right? And I'm like, well, I got a bash script too, right? David over there's raising it. Neil's raising his hand. We all have bash scripts. That's great. I feel Python's probably a little bit better. So, and I write just good enough Python to be dangerous. So that kind of fit my my needs there. So. Yep. Yeah, and also too, a lot of it is I've been writing a lot of Plumi, Python and Plumi, and interfacing with butane. There is, you can consume BUPY as a module, get access to all the functions, and be able to launch infrastructure with Plumi and be, extremely productive. So you can see the progression of what you're trying to launch in a cloud provider or wherever on your laptop. And once it's like, okay, you can then use something like Plumi with BUPY as a module, import it in and be able to launch, process the ignition, feed it variables. And, life is pretty great in Jinja for the most part. So any other questions? You all are the best. Thank you so much. I don't know what happened. I would have been 25 minutes spot on. That was 1:50 on the YouTube video. It's all right. It's just